Greetings. Welcome. So today is December 17th, and I would like to wish everyone happy holidays, a Merry Christmas, and a New Year. I would say a Happy New Year, but the way things are going, foreign policy, and let's just see if we get a new year, and then we can try and work on making it better, huh? Where last I left off, a video like, I don't know, it was like months ago or something now, I was working with a bitoroidal transformer, and to make a long story short, I suddenly got sick of it. I just realized I was sick to death of it. I had trouble with some of the battery charging, and I think I know what's going on and whatnot. But for even towards the end of when I was working on that, I kept thinking about there are other things I really want to work on. And so that's what I'm starting on now. And this is going back to doing more sort of basic research. So I'm calling this Project Q. It's kind of James Bond-like. But it's going to be basically a moron doing a deep dive on Q factor. I don't want to be like trying to be too self-effacing, but someone with no background in electronics, no like work experience in electronics, I'm just looking at this stuff myself and looking at how do you improve Q factor. And Q factor is where the way I'm using it is the oscillation of a capacitor and an inductor and an LC tank circuit. So this is going to be just barrels of fun. And in this video, I'll just sort of give you the lay of the land, and also we'll look at a few sort of oscilloscope tracings to demonstrate what I'm talking about, and just talk through a little bit of theory, and I'm going to talk about it at a spreadsheet for a while too, but if you want to understand what I'm getting at, it's probably worth listening to it all. So, as the NC. Sorry, I'll try to cover it quickly. So, where to begin? To try and go through it quickly. You have an LC tank circuit where you have your cap and your inductor, and they oscillate back and forth. And how do you make that oscillation as undamped as possible? Now, this is mainly empirical knowledge that I kind of just throwing time at this, I kind of stumbled into. And again, I don't have the background on this, but when you have a shorter and shorter pulse, or a smaller and smaller cap, the oscillation becomes less and less damped for a given coil, up to a point where it all just skates sideways. And it seemingly always just skates sideways. So it doesn't matter, sometimes it's at 5 kilohertz, sometimes it's at 30 kilohertz, it just starts skating sideways. So it's like, what the hell is going on? Why does it always do that? You're like, oh, I got it's 95%. No, that's as good as you do. So what's going on there? Now, there are sort of two questions. First is, why is it getting better when you're doing the briefer pulse? And that would be a whole video in itself. But just suffice it to say that it does, and you're making more efficient use of your coulombs of charge as you're doing a briefer pulse for establishing a magnetic field. And second is that what is important is the pulse duration divided by the tau time of the coil. That ratio that determines how the thing improves, but it always goes sideways. So why is it doing that? And these are topics we're going to be talking a lot about going forward. Most obviously, but I would say the most reasonable guess, it's because of two things. One is skin effect. Two is don't want to do that without the other. Two is proximity effect. So skin effect, proximity effect. What is the net effect? of these effects. Allow myself to introduce myself. The net effect is they introduce additional resistance, and introduction of additional resistance changes the tau time, changes the ratio of the tau time, and things get worse. Let me just shut up and we'll talk about a spreadsheet for a while, then we'll do some stuff on the oscilloscope, and then in the next video we'll talk about skin effect and proximity effect, and we'll talk about you know, how I think Tesla got around it, and what I'm working on to try to get around it with a 3D printer. Okay, here we go. So just to sort of dip our toe in the pool here real quick, and this is work that I've done before. In a moment I'll show it on the oscilloscope, but for now let's just talk about it real quick. And this is work I've done before. Mainly what I wanted to get an answer to here was it possible, when I was no longer seeing improvement, that the cap was just leaking out through the oscilloscope? And the answer to that was no. But let's just go through this real quick. So I have this big red coil. It's 10 pounds. I think it's 16 gauge wire. The measured induction is 92 millihenries. And let's say we put a 10 UF cap and pulse the 10 UF cap into it. When you do that, at what frequency will the cap and coil oscillate at? What frequency will they resonate at? And that's 1 over 2 pi times the square root of this and this. And therefore the time for one full wavelength is 2 pi times the square root of LC. So this looks a little busy, but it's not that complicated. So here's 92.5 millihenries, that's the henries. This is microfarads, that's the farads. This is this times this. This is the square root of that, that's pi. So this then is the, what the heck is this? This is, I don't know, I think it's, yeah, this is the time for one full wavelength in seconds. 1 over that gives you the resonant frequency. So this cap in this coil, it's 165 hertz. That's the time in milliseconds for a full wavelength. A half wavelength is where the cap will go most negative. A quarter wavelength is where the cap will be discharged to 0. And a few more things here. This 12 waves is one full wavelength times 12. So in 72.51 milliseconds is where the thing would oscillate 12 times. Now over here we're dealing with the resistance in the system. This is the resistance in the coil. This is nothing. It was just measured on a cheaper meter, so I trust this one. This is the resistance in our switch, 130 milliohms. For a while I was adding resistors just to have fun and look at how quickly it damped out, and there'll be another use for this later on. So the total resistance is this plus this. So now we can think about a few more things. If we have the resistance and the induction, then we know the tau time of the coil, right? Because the tau time is induction over resistance. And you see that's constant. It's independent of the cap that we use. Now what does the tau time of the coil tell us? It tells us that in 1 tau time, under a situation of constant voltage, the magnetic field strength of your coil will reach 63% of its maximum. We also know the pulse duration that we're hitting the coil with the cap. Now when I look at the spreadsheet now, I see I made a mistake because I'm saying that the spreadsheet is half wave. Half wave is where the cap goes as most negative. The actual pulse duration is quarter wave. That's when the cap discharges fully. But it's not entirely, it doesn't matter. You could use this value, or this value, but I'll fix that going forward. And then this is the ratio of the pulse duration divided by the tau time. And I'll just tell you, just a moment, that at first, the smaller this ratio gets of your pulse duration over your tau time, the better you do with how far negative your cap ends up after 1/2 wave, or in other words, how good of a Q factor that you have. Now, the explanation for that would take a little time to go into, but in a nutshell, it's that with the shorter and shorter pulse in comparison to the tau time, you make more and more efficient use of your coulombs of charge. So in other words, when you do a briefer pulse, you're of course going to get a weaker magnetic field, but for the amount of charge that you expend to get a given magnetic field, you make more efficient use of your coulombs of charge as you go faster. And that has to do with the equations for instantaneous amp flow. And you can go on a site like Electronics Tutorials, look up those equations and put it in a spreadsheet and see that that's true. And it's also true that it seems like that would continue in perpetuity. So initially you start to get some improvement, and then just right when it starts getting interesting, and you see this with lots of coils, everything starts skating sideways. So why is that? And as far as I can discern, there are two reasons for that, and they both boil down to one thing, and that is that you end up, when you're going faster and faster, getting two new sources of resistance that start to come into play. And those are skin effect and those are proximity effect. And we'll talk about both of them in a moment. But first, let's just demonstrate this. I'm not going to do it with the meter. We'll just put it on the oscilloscope and look at a few different coils as we go faster and faster. And it improves up to a point that it doesn't improve anymore, and then it starts getting worse. So here we have a coil. I've got 20 UF of capacitance, and it's discharging through that switch there. Now if we put 20 UF in, then the nice thing is it calculates everything for us. So there's our resonant frequency. If we let it run for 103 milliseconds, we'll get 12 full waves. And this is the ratio then of the pulse time over the tau time. So let's just throw 10 volts at it. And that's what it looks like. Now, I could go and measure, and we'd see that it would be a bit less than 8.99. And that's what it looks like. So now let's take one of these out. So instead of 20, it'll be 10. So again, that's what it looks like at 20. When we go to 10, now we just need to change that value to 73 in order for it to be 12 waves. So 73, recompile. So that's what it looks like at 10 UF. So now let's go to 4.7. And that's what 4.7 looks like. Now let's do 2.2. And that's what 2.2 looks like. So looking better. Let's try 1. So there's 1 UF. It looks even a bit better. So isn't this neat now? Now let's go to 0.1 UF. There's 0.1 UF, which it might be a little bit better. It's not dramatic, but it's probably a little bit better than 1. Let's go to 0.01 UF. So there's 0.01 UF. Wah, wah. So now it's getting worse. So the thing that I wanted to do was figure out, is it leaking out? And you have 10 mega ohms of resistance here, and we're at 10 volts, so it's a 1 microamp draw. And you can do the math and you can figure out, no, it's not leaking out that much. And the other thing you can do is just leave this thing here, not charged, just sitting there with this thing hooked up. And you can see it leak out over a couple seconds. But our frequency, we're at 4.4 kilohertz. So this is occurring in like 10 milliseconds, somewhere around there. Actually, I have it written down. It's 2 milliseconds. So there's not time enough for it to be leaking out. So it is, in fact, getting worse now. And why is that? So I'll tell you why I think it is. And first we need to go to the American wire gauge chart. Well, even before then, even when we're at 0.01, again, we're only running at about 5 kilohertz. It's not that fast. And if we go to the American wire gauge chart, this is, I believe, 16 gauge. And so maximum frequency for 100% skin depth for a solid conductor, 11 kilohertz. So in other words, we shouldn't be running into significant skin effect yet. It would have to be going about twice as fast. So if we're not running into skin effect, what is it? And I would say that we're running into proximity effect. And that's the interaction of each wire with the wires adjacent to it, both in the layers and the ones next to it. That'll be the topic of the next video, but just as a quick background. So I have this LCR meter, and right now I have it hooked up to a resistor and LCR, so now it's measuring resistance, and it measures at either 120 hertz or the other is 1,000 hertz, 1 kilohertz, and you adjust with frequency. So the two values are pretty much exactly the same. However, I noticed with this thing, whenever I tried to measure the resistance in a coil, it would get all goofy. I was thinking, where are these guys at Exitech trying to sell me? When I measure the resistance in this coil at a frequency of 120 hertz, it gives me 5.37 ohms. That's right around what I measured with the multimeter, 5.5. Now if we go to 1,000 ohms, 9.5, 9.6. So what I eventually realized was, good gosh, that actually is the resistance of that coil at 1,000 hertz. And 1,000 hertz is, slower than 5,000. So it's not skin effect. This is proximity effect. So now we know two things. We know that the proximity effect is predominant, and we see it kicking in even at 1,000 hertz. So if we go back to the spreadsheet, we can put in 0.03, and that gives us where am I? 0.3 gives us a frequency of 955, so around 1,000. So even at 0.3, the resistance was a lot higher than I was thinking. And that's why you saw a great improvement from 10 to 1, and then 1 to 0.1, it didn't really do anything. It didn't get much better, it didn't get much worse. And then going past that, it was just falling off the edge of a cliff, getting worse. And that's because the resistance from proximity effect is increasing, and hence this tau time is no longer constant. The tau time is decreasing, and all of this changes. So in the next video, we'll do a little bit of a deep dive on skin effect and proximity effect. At least a deep dive from someone with no electronics background, no electronics work. Doesn't really have any clue what he's talking about. but we'll look at those two a bit more closely.
And the last thing I'll show you, and then we'll wrap the video up, is, you know, there was the LCR meter, and I could see the change in resistance between 120 hertz and 1 kilohertz. And I also have some ideas for mitigating both proximity effect and skin effect. And one of the ways you see is that, you know, the Q factor should improve. But it would be nice to be able to measure things. You know, that I can look at 120 hertz, the resistance, 1 kilohertz. I'd like to measure more than that. And I found all these really expensive things. And then let me show you what I found here. Look at this. LCR handheld bridge, continuously, where are we? Continuously adjustable from 100 hertz to 100 kilohertz. Perfect. And it lets you adjust it 1 hertz at a time. So in other words, you put in the cap and you know what the resonant frequency is. And so you could just set the LCR for what's the actual impedance there. What, you know, what's the reactive resistance plus the straight line DC resistance. So I have a strong hunch what Santa's going to be leaving for me this Christmas. Most of the things that I saw like this, I mean, this is out of China, but you know, the stuff works. And most of these cost like $2,000, and they look like this. So this is something I'm really looking forward to. And in the next video, we'll talk about, as I said, we'll talk about the proximity effect, the skin effect, and what might be done to try to work around those. So stay healthy, everyone, and talk to you later.